All right. Let's talk about line integrals, and then we're going to be talking about Green's theorem. So 2 sections, 13.3 and 13.4. So sections we'll be going over are 13.3 and 13.4. Okay. All right. Let's talk about line integrals of vector fields. Okay. So given a vector field f, it's a function of x, y, z. All right, and we can give it a vector equation p, q, r, where these are each functions of x, y, and z, and there's the I, j, k components. Okay, so let's say that f is a continuous force field or a continuous vector field that represents a force. So f is a continuous force field, and it's clearly in R3. And an example of this would be the gravitational field, the gravitational force field. Let's compute the work done. Let's compute the work done on some type of particle that is being forced to move in such a force field. So there's a force field, and we're grabbing this particle, and we're making it move through this field. And what we're interested in is computing the force. So here's the particle. It's moving along this trajectory, some curve C, okay? And we can partition this curve C to a bunch of points. Here's some P naught. Here's some independent perimeter space ranging from A to B. Clearly, the initial parameter maps to P naught. Then you go all the way, and you get like some Pi minus 1 and some Pi, and you get some Pi star, where Pi star, this is equal to some Xi star, Yi star, and you can think of that as like the mapped average between Pi and Pi minus 1. Okay, and we can say chop up all of these arc lengths. Okay, let's say all of these are arc lengths. And we'll say one of these is some DSI, the ice arc length. Okay, what can we say? Well, we could say here at Pi star that there's a tangent vector to it, and there's a unit tangent vector here. Furthermore, we can say that there's a force vector here. So I can remove this. We know what P star is. This is the tangent vector, or the unit tangent vector, T of some Ti star. And over here, let's say here's our force vector, F of our Xi, Yi, and Zi. So this is F evaluated at Xi star, Yi star, Zi star. Okay. Notice that if delta Si is sufficiently small, then it seems like the path right here, this little tiny bit, if I can put it in a different color. Notice that the path seems like it is purely moving along the direction of the tangent unit vector T, capital T. So we make the assumption that for delta Si sufficiently small, a sufficiently small increment moved across the curve C, that we can actually model the position of this particle moving through a force field, that its direction of motion is identical to the tangential unit vector. That is an assumption that we will make. Okay? And so now we can calculate the work, because recall work was equal to F dot your displacement, right? Well, our displacement is that increment. It's that delta Si. But For it to become a vector, like the displacement vector, we need to give it a direction, and we'll give it the direction of the tangential unit vector because of the things that we stated earlier, that for a small enough increment of movement, that the particle is actually moving in the direction of the tangent line, the tangent vector. And don't forget, how do we get T, capital T? The unit tangent vectors remind you of derivatives. So we got that T prime there, because T prime is the derivative, and that's the slope of the tangent. It gives you the function that's tangential. But because it's a unit tangent vector, we must unitize it like so. Okay? And as you can see, that's why it's a function of T. So we can calculate work. This ends up becoming xi star, yi star, zi star. And we're going to dot it with what will replace this displacement vector. The amount, the magnitude is this delta Si. The direction in which it goes in is that T. And let's say Ti star. All right. So bringing our calculation over here, what we end up getting is then this ends up equaling when that's one, this is the ith work. We call it work sub I. This is the ith amount of work. So to get the work total, we can approximate it as the sum from I equals 1 to n of all of these sums. Xi star, yi star, zi star, dot, and delta Si, T, and we can replace Ti star with Xi star, yi star, and Zi star. And why is that? Well, T is a parameter, and all of our functions in X, Y, and Z are functions of T. So we can just plug in what that T is and evaluate the X, Y, and Z. All right. And so when we take the limits as n approaches infinity of this guy, this whole expression here, what are we going to end up getting? We're going to get the actual work, the real bona fide work. And that's the line integral C of f dot T ds. Okay. So quite a lot on this board, okay? There's quite a lot on this board, but if you follow along, it's not that bad, okay? So right now we're talking about line integrals inside vector fields. So the vector field is now, in this case, a force field, like let's say gravity, because gravity is a force. It can be modeled as a force, and the force is a vector, and so we're talking about vector fields, and so we're doing line integrals in vector fields. And so if we wanted to calculate the work, this is how we would go about it. Okay. So to succinctly conclude that the work now can be thought of as evaluating the function like so. And I'll explain why we write it like this in a second. Okay. So the reason we can write the work as this now is because over here, this is the definition of our T. Okay. We had originally that work is the integral, the line integral of f dot T d. These are all functions of s, ds arc length. But we're replacing f with f of r of t because f is a function of x, y, and z. But if we can define some r of t, where it's some p, q, and r, where these are all corresponding functions of x, y, and z, we can pick all the x, y's, and z's. That corresponds to a parameter t. Plug it in, and you just get an r of t. So we can succinctly represent this f as some f of r of t. Okay, kind of change it as the parameter. And so these are just equivalent expressions where a and b tells you what parameter space changes, the a and the b. Okay. So once we have that, we realize that this breaks down when you cancel these guys just to this. That's how we can compute the work. Okay. Where don't forget this, like f of r t is the same thing as our f of some x of t, y of t, z of t, because this is precisely the definition of some r of t. And another thing we'd like to define is that r prime of t can also, it's that dr. dr can be defined as r prime of t dt. This is another thing we want to define here. Okay. Because we're going to be able to re-express line integrals in another formulation using a vector equation instead of a parametric equation. All right. Let's say that your t ranges from a to b. Okay. Your line integral can actually be represented as some f dot dr. And if you place dr and that f with this fr of t, you'd restore the original line integral formulation that you had earlier. Okay. So let's use all this information here to do a concrete example. That's what you guys will be expected to do on the test, right? I don't need you. This is not a class where we expect of you to derive these things. There are classes like that, and they're really fun. But let's talk about what we got to do for this class. So let's find the work from the force field given by this equation f of some xy. It's given by some x squared minus xy of a moving particle moving along a quarter circle. So this particle has a vector function for its position that is like so. And here we go right here. Let's say it ranges from 0 to pi over 2. That's where the parameter t ranges from. So if cosine is parameterizing its x movement, sine is parameterizing its y movement, and t is a parameter that goes from 0 to pi over 2, it's pretty clear that this thing is moving in some type of circular fashion. So if pi over 2 is a quarter of the rotation of the circle, this forms a quarter circle. All right. So this is what we get here. And this is our r of t. It's a circle of radius 1, clearly. What we want to know is what is the work done for moving a particle in a quarter circle like that in this vector field given by this equation. So what we want to do is we want to find work. And in this case, this is the line integral of f dot dr. Okay. Then we notice that this equals the integral from 0 to pi over 2 of some f of r of t dot r prime of t dt. So we just have to find these expressions in the integrand to be able to calculate the integral. So what is r prime of t? It's just the derivative of this guy, d dt. Derivative of cosine is negative sine. Derivative of sine is cosine. Done. We found r prime of t. So what is f of r of t? Well, this is r of t. This is f of xy. We just plug in for every x we see in this a cosine of t, and for every y we see a sine of t. So this implies that our f of this vector function, because f is a function that takes in vectors and spits out other vectors. Okay, so we're giving it what it wants. We're inputting a vector and we're going to get out another vector. So that's the vector that gets. So to evaluate the integral, first we got to take the dot product between these two vectors. So when we take the dot product, we multiply the components and then add. So this becomes cosine squared t sine t with a negative on it, plus negative cosine squared t sine of t. So notice that these are the same thing, just with a negative out in front. So this becomes negative 2 cosine squared t sine of t. And this is what we're supposed to integrate, because that's what's in the integrand. So let's take the integral of that guy. Well, we know we can use u substitution. Let u equal cosine of t. That implies du dt, derivative of cosine is negative sine of t. Well, that implies that du is equal to negative sine of t dt. Oh, that implies that dt is equal to negative du over sine of t. Oh, well, that implies that when we plug it in back into our integral and we do u substitution, what do we get? We get that this is negative 2 integral of 0 to pi over 2 of u squared sine of t times this negative du over sine of t. Cancel out the signs of t's, and you just have this expression negative 2. Oh, the negative becomes a positive because these negatives cancel out. Integral 0 pi over 2 u squared du. So when you integrate, this becomes a negative 2u cubed all over 3. Evaluate at 0 pi over 2. But this is the same thing as 2 over 3 when you factor it out of our, what was our u cosine of t cubed, evaluated from 0 to pi over 2. So this just becomes 2/3 times cosine of pi over 2 cubed minus cosine of 0 cubed. Cosine of pi over 2 is 0. Cosine of 0 is 1. When you cube it, it's 1. When you put a negative on it, it becomes a negative 1. Negative 1 times a negative 1 times 2/3 ends up giving me a negative 2/3. So this is precisely the work done by moving that particle a quarter circle in this force field. This one right here. So it's not that bad. The mathematics to create, the ideas that went into creating this is pretty hefty. Not gonna lie. As a mathematician, I'll tell you, it's pretty hefty. But using it for your guys' purposes is not that bad. Does it help to know where it comes from? Absolutely. It gives you an intuition for what's going on and what you're doing. But it's not necessary. But I, as a mathematician, I want to show you what this stuff is. And show you how to use it. Okay? That's really important. So I will make a note that notice that the line integral of f dot dr. Notice that this is the same thing as the line integral of f dot t ds. Okay, remember they're equivalent. But notice this thing, that the line integral going in reverse of f dot dr is equal to the negative of the line integral of f dot dr. Why is this the case? This means if you decide to go, let's say you're moving in some path C like this. Okay, if you decide to go this way, you'll get one answer. But if you decide to go into the reverse like this, negative C, you get the negative of the answer you got before. That's what that's saying. Meaning the orientation you take, whether you go clockwise or counterclockwise, will put a minus sign on your line integral. So we'll make sure we keep that in mind. Okay, here's another example. Let's do this line integral. What does this equal if we have a vector field given by xy, yz, zx, and let's parameterize x as a t, y as a t squared, and z as a t cubed, meaning our vector function f of r of t then just becomes xy, which is t times t squared, which is t cubed, yz, which is t squared times t cubed, which is t to the fifth, and xz, which is t times t to the third, which becomes t to the fourth. All right. And notice that this implies that our r of t is this t squared, t cubed. And so our prime of t is the derivative with respect to t. So this becomes 1, 2t, 3t squared. So this is the same thing as the integral of f of r of t dot r prime of t. We've got to put a vector here, dt. That's the same thing as taking the dot product between this guy and this guy. So when we do that, what do we get? This is the integrand. This is the integrand of that integral. So this ends up becoming 1 times t cubed, which is t cubed, 2t times t to the fifth, which becomes 2t to the sixth, plus t to the fourth times 3t squared, which is 3t to the sixth. We regroup the terms and we get t cubed plus 5t to the sixth. Okay. So then we take the integral of this guy, integral of t cubed plus 5t to the sixth. Notice that we didn't say where does t range from. T is a free parameter in this case. Or is it? Okay. If we don't say where t ranges from, then we do the integral as a free parameter. But if we want to actually say, hey, let t only range from this parameter, then that's what we'll do. I have not put it up here, but I can now. Let's say that t, let's actually have it range from 0 to 1, so that our integral becomes a definite integral. And so this will range from 0 to 1 as well. And we'll put a dt. So let's compute the integral. This becomes t to the fourth over 4 plus 5t to the seventh divided by 7, all evaluated from 0 to 1. Once you do the computations and evaluate, what you end up getting is this reduces to 27 over 28. Now let's talk about line integrals of vector fields and scalar fields. Okay, recall we start out with some vector function of x, y, and z by saying that it's equal to some functions like that, where p, q, and r are functions of x, y, and z respectively. And then our line integral can then be expressed as an integral from a to b of our f of r of t dot r prime of t dt. Okay, but notice, what does this mean? R prime of t is actually equal to, if some x prime of t, y prime of t, and z prime of t, because r of t was just some x, y, and z of t all respectively. So what happens here is when you get this, you get that this equals the integral from a to b of your p times your x prime of t plus your q times your y prime of t plus your r times your z prime of t dt. But notice this is the same thing as the integral from a to b of p dx dt plus q dy dt plus r dz dt t. Notice what happens when you factor out a dt. When I factor out a dt out of all these guys, it cancels out with this dt out here because this dt is really multiplied times all of these. There's some understood to be there, but neglected to write parentheses. So when you cancel out the dt comes here, and this just becomes a dx, dy, dz, and you get a 1 over dt over here, and it cancels out with this dt. So you get that ends up equaling the integral from a to b of some p dx plus some q dy plus some r dz. This equals that. Our arbitrary line integral equals that. So this allows us to come to section 3.3. All right. Before we were kind of talking about 13.3, and before we were talking about actually some 13.2 stuff. Now we're really at 13.3. We're going to talk about the fundamental theorem of line integrals. Okay. It says, recall from the fundamental theorem of calculus, part 2, the original fundamental theorem of calculus that you guys are familiar with, is that the derivative undoes the integral. Right? Because look, this f prime of x, this is the same thing as saying d dx of f of x. And so d dx and the integral, they meet up and they destroy each other. And all that remains is the f of x. And you evaluate it from the limits of integration. Okay, that's the fundamental theorem of calculus. Now, line integrals, because they're their own special kind of integrals, have their own fundamental theorem. Okay, and to talk about it, we kind of have to set up some groundwork. So let's say you have a three-dimensional situation. Like so. Here's some A of x1, y1, z1, your first starting spot, and your B of some x2, y2, z2, your ending spots. And this is their x, y, z. And this is some three-dimensional curve, a space curve. All right. The fundamental theorem of line integrals says this. That's that. What is this gradient little f? I thought we were talking about line integrals like so. Where's this gradient little f coming from? Well, recall, if you have a conservative vector field, if f is a vector field that is conservative, recall that means it can be expressed as the gradient of some potential function, some scalar potential function f. Meaning this, it's not a scalar function, meaning it has scalar values. It means you can evaluate it and it'll output a scalar, it'll output a number. It won't output vectors. Okay, that's the point. That when you give it an input, it outputs numbers, not vectors. So here, then we can take the gradient of such a function. And if you have a conservative vector field, it by definition means that you have some potential function such that the gradient of such potential function equals the vector field. Okay. So that's why we can replace this capital F with this gradient of F vector. Okay. And this is actually the statement of the fundamental theorem of line integrals. Let's prove it because it's so important. We got to prove it. Okay. Notice that this is the same thing as this. Is it not? Yeah, it is. Oh, but when we apply the definition of the gradient, recall that the gradient of a function is just partial f, partial x, partial f, partial y, and partial f, partial z. So when we input the gradient, when we put the r of t, where r of t, remember, is just some x of t, y of t, z of t. When these guys meet up, when you take the dot product, when you put them and then take the dot product and we meet up, notice that then r prime of t is the derivative of these guys. When they meet up and you take the dot product and you input this into there, what you get is this guy, partial f, partial x, meeting up with x prime, which is dx dt, plus partial f, partial y, meeting up with y prime, which is dy dt, plus partial f, partial z, meeting up with z prime, which is d z dt. All of this had a dt multiplied times it. This sure does look like some kind of chain rule, does it not? Yeah, matter of fact, we can pull out a dt we can pull out a dt from the denominator here. So this is the integral a of b. We can pull out a ddt of partial f, partial x plus partial f, partial y plus partial f, partial z is z dt. But look, ddt, there's a dt there. Fundamental theorem of calculus says that the integral goes away. Okay? And not only does the integral go away, but we can determine what the evaluated value of this expression is by saying that this is the f of some r of your endpoint b minus the f of some r of your endpoint beginning point a, by just applying the fundamental theorem of calculus for line integrals. And so we're done. It wasn't that bad. Let's find work. And let's be given the vector field of the gravitational field. Nope, it's going to be Q there. So let's find the work of a particle moving with mass m. Maybe it's an electron. And let's say it's moving from the point 3, 4, 12 to the point 2, 2, and a 0 along the piecewise smooth curve C. All your curves you'll be given will be piecewise smooth. You don't have to worry about them not being piecewise smooth. Let's show that this is true. Meaning, if we show that this is true, this implies let's prove that gravitation, the force of gravity, is conservative. what we have been given is the vector field. What we aspire to find is the potential function of said vector field. The potential function is lowercase f. It is the function such that when you take its gradient, it reproduces the vector field, or in this case, the force field of gravity. Okay? Notice that it can be shown, and we will show, that such a potential function is this. And we've talked about this before. I don't feel bad about just bringing it up again. We've talked about this in a previous class. Okay? Where f is the potential function. So the work, which is defined as the line integral of f dot dr, is the same thing when we replace f with its gradient counterpart, like so. Oh, but the fundamental theorem of line integrals, which utilizes the fundamental theorem of calculus as an implication, gives us, well, the implication of the fundamental theorem of calculus allows us to imply the fundamental theorem of line integrals, which means that this ends up becoming f of the final 2, 2, 0 minus f of the initial 3, 4, and 12. What happens when you input these values? You just get m, capital M, G all over square root of 2 squared plus 2 squared plus 0 squared minus m, G divided by square root of 3 squared plus 4 squared plus 12 squared. What you end up getting when you're done calculating is m, capital M, G times 1 over 2 root 2 minus 1 over 13, where little m is the mass of the electron, for instance, and capital M is the mass of our planets, Earth, and G is just a gravitational constant that has been discovered using the Cavendish experiment. It was an experiment that utilized a double pendulum to calculate what is the constant, the gravitational coupling constant, G. Let's talk about path independence. What does this mean? Well, it means the line integral doesn't change based off of the path that you take. So here's a point B, here's a point A. I can get to point B and point A taking all kinds of different paths. Let's say this is path 1, this is path 2, or C1 and C2. Okay? If you are in a conservative vector field, okay, the conservative vector field gives you this astonishing equation. That the line integral of either of those paths is the same. Meaning the only thing that contributes to the value of the line integral is what is the value here at A and what is the value here at B. It doesn't matter whatever path you take. I could have taken this path, path C, 3. In a conservative vector field, even this will hold true. Okay. Now let's talk about what is a closed curve. A closed curve or path is one such that where you start is also where you finish. So this is a closed path. Because if I call this from C1 if I just call this some curve C, its beginning and its end are at the same location. So this is called a closed curve. So if the line integral's value is path independent, what does that mean? Well, guess what? Being in a conservative vector field gives you the fact that it's path independent. So, meaning this curve can be modified to going like some C1 to here and some C2 here. So we broke up C into C1 and C2, okay? But it doesn't matter because C1 then C2 is the same thing as C. So notice that this line integral is the same thing as okay. They're the same thing. But here's the crazy part. That is actually equivalent to this. Why is that the case? Well, recall that the value of a line integral, if you go in the reverse direction, is the minus of the original value. Okay, so that's why this right here is why this equation holds. Okay, but notice that when we utilize the fundamental theorem of line integrals, this equation right here, when utilizing the fundamental theorem of line integrals, says that, oh, well, f of r of, notice that C1, it goes from A to B, so the final is B, the initial is A, so that's this piece. And now, notice that this equation is the same thing as this equation, and notice that this, we're going to add it to our C2, which its final, C2, its final is A, its initial is B. Minus initial. Right? Oh, but look, this is so crazy and beautiful that these cancel and these cancel. So this ends up equaling 0. So if these two are the same thing as these two, which equals 0, then these guys equal 0, meaning if I set this equation equal to 0 and add one of these integrals to both sides, that means I get positive negative C2 . Okay, what does this mean? Well, it means conservative vector field implies path independence, and path independence implies conservative vector field. Okay, because conversely, we could say because now what we did is we showed that path independence implied conservative vector field. And it can be shown, I won't go through the details, but they're very similar. This is a very similar argument that if you have this to be true, okay, you can actually derive the fact that you have independence of path, because you can say, oh yeah, this integral is just C1 this plus C2 this, reverse it and go all the way the other direction. You end up at the same conclusion. So we have now shown an if and only if statement. And that this stuff, being able to prove this stuff will not be on your exam, so I won't take too much time with this. So what do you guys get? Here's your theorem. That if is independent of path, that implies that it's equal to 0 for every closed curve. Every closed curve C. Okay. Another theorem that we won't prove is that if F is a conservative vector field, that implies that there exists this potential function such that the gradient of this potential function is equal to the vector field. Okay, so another theorem that we won't prove, coming right up. Another theorem that we won't prove that will be highly useful. Some of them I do prove, some of them I don't, and some of them I have proved, like this one we just did earlier. Here's another theorem. Let's say if your vector function of xy is given to you by functions of p of xy, and f is conservative, and p and q have continuous first order partial derivatives on some domain D, we get this thing, partial p, partial y equaling partial q, partial x. So, meaning if you have a conservative vector field and these partial derivatives exist, then this is going to happen. Okay. Now, let's define what simply connected regions are. A simply connected region is a region like so, this region D. It's simply connected, okay? Because any loops we form, we can get them smaller and smaller and smaller, and we won't have to stop. But notice a space like this that has holes in it. If I formed a loop around these holes, I couldn't contract it to a point. But if I can form a loop in this space, I can contract it to a point right here by just taking a straight line and contracting to a point. But over here, we can't do that, and we fall into an empty hole. So you have a simply connected space if it's like this, and a non-simply connected space if it's like that. You'll never be dealing with a space like this for your class. So you don't have to worry about that. So assuming you have the kind of space you'll always be given in this class, here's a theorem that you can use. Your function, if your vector field is some PQ, okay, and it's defined on an open, simply connected region D, and P and Q have continuous first order partial derivatives throughout. You know this is true by this theorem, but guess what? If you're like so, and you have this region, this implies you have a conservative vector field. Meaning that there exists some f such that when you take its gradient, it equals your vector field. So if you want to know if a vector field is conservative or not, you should be given the conditions to try and use this theorem. Check whether this is true. If this is true, it's conservative. If it's conservative, you get this. If it's this, you get that cool stuff with the line integrals that allows you to state that, oh, path independence. It doesn't matter what path I take. The value of the line integral only depends on the endpoints. Very much like the fundamental theorem of calculus, where the value of the integral only depended on the value of the antiderivative evaluated at the endpoints. So let's do some examples. What if we have this vector field like so? Is it conservative or not? Well, we could just let this be P, let this be Q. Does partial P, partial X, whatever it equals, does it equal partial Q, partial Y? Oh, I switched these. This should say Y, and this should say X. Do they equal? Well, partial P, partial Y is a -1. Partial Q, partial X is a +1. They don't equal. F is not conservative. We don't really, okay, that's all we got to say. Let's try a different one. What if it's this? Is this a conservative vector field? Let this be our P, let this be our Q. Let's take partial Q, partial X. That's 2X. Let's take partial P, partial Y. That is just 2X. Notice they're the same. Haha. This is a conservative vector field. Why do we like the conservative ones? Well, it's because they have all these good theorem properties. Okay, now let's take this situation with this conservative vector field that we have here. That the theorem has told us, yeah, this is a conservative vector field, meaning there exists some potential function such that the gradient of this potential function equals this vector field. Well, let's find the potential function. Why don't we? Well, notice that the gradient of f, if it were to equal capital F, this is the same thing as partial f, partial x, comma, partial f, partial y, bracket, bracket, is equal to your p of xy, q of xy. Does it not? Well, if that's the case, what is this partial f, partial x? Well, partial f, partial x is just taking the derivative of a function, okay? And we know what partial f, partial x is because we know it should equal this. How did we even set this equal to that, which equals to this? Well, it's because we know it's a conservative vector field by the theorem, and that we know that this is true. So that allows us to set this equality to hold. Next, what can we do? We can integrate both sides. Okay, so once you integrate both sides, what you end up getting, let's do it dx, dx. What you end up getting here is that your function f of xy is the integral of this stuff dx. Okay, But what does that end up becoming? That's just 3x plus 2x squared y, everything over 2, okay, plus some g of y. This is a function of y. It exists because when we took the derivative of both sides here, we got here. And we could have had any kind of function of y, because once we took the derivative of it, it would have gone away. The derivative treats it as a constant. It would have just gone away. So that's why we put that g of y, because theoretically it existed and it was there. It could possibly be there. So when we cancel out these 2's, we get our f of xy is equal to 3x plus x squared y plus our g of y. This is our f of xy. Okay, now what? Well, there's a lot you can do from this point, because take note. What about if we also use the fact that we know partial f partial y is equal to q, which is equal to this? Oh, yeah. What if we do that, right? Well, if that's our partial f partial y, notice that this is equal to some x squared plus some g prime of y. How do we know that? Oh, that's because we found our f of xy right here. If we took partial y of this, that's the same thing as taking partial y of this. And partial y of this makes this become equal to that. Aha! So what does that mean? Well, that means g prime of y is that negative 3y squared. And this is very important. You should know how to derive a potential function. Okay? Because now, what can you do? You can integrate. So you just get g of y is the integral of this with respect to y. So you get negative 3y cubed all over 3. Cancel out 3. You get negative y cubed. And this is your g of y. So we can construct our potential function f of xy, because now we know what g of y is. So it's going to end up becoming 3x plus x squared y plus what we know g of y was, this negative y cubed. Boom. And we found a potential function. Don't forget, we can actually, once we integrate, put an integration constant k here, put an integration constant k here, and put an integration constant k here. So in general, what we had was true for k equals 0, but to be true in full generality, we'll include that integration constant k. So there you go. Now you know, given the conservative vector field, how to find the potential function. So what does this mean? Well, what we can do is we can now evaluate the line integral of the very f that we've been talking about. Let's say that it traverses some type of curve governed by this parametric equation. And let's say t ranges from 0 to pi. We know that the line integral may be re-expressed as this, as a consequence of the fundamental theorem of line integrals. Initial and final values. Well, we know that that's equal to f of 0 comma negative e to the pi minus f of 0, 1. Notice that this ends up giving us e to the 3 pi plus 1. Okay. What are we doing? We're plugging it into f. That's it. This f, the f that we found. It makes it so easy to calculate the line integral by using this mathematics here. Okay. Moving on to our last to the last section in this video. Not our last section in calculus 3, not by any means. We still have divergence and curl and the divergence theorem and surface integrals. But now we're going to be talking about Green's theorem, a monumental discovery of the human mind, made by someone who wasn't even someone you could call a mathematician by trade. This man, Green, was just a baker all his life. He just did math for fun once he was done baking stuff. And he laid the groundwork to create the mathematics of electricity and magnetism that led to Maxwell's equations. What does that say? It just tells you that there's no excuse in life. This dude was baking bread and also inventing incredible ideas in mathematics. Let's talk about Green's theorem. This is a statement about relating line integrals with double integrals. Let's say we have a positively oriented curve about some region D. This is a positively oriented. All that means is the region D is always on your left if you traverse the curve, which means it's always going tick, 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 counterclockwise. The curve goes in a counterclockwise traversal. We will not prove Green's theorem, unfortunately. That's beyond the scope of this class. But let's say we have a positively oriented, piecewise smooth, simply closed curve in the plane and let D be the region bounded by C. If P and Q have continuous partials on the region D, then we can say that the line integral, and this is a new fancy notation for line integral, is equal to this. So it correlates how to find a line integral with a double integral. Okay. And Green's theorem is extremely powerful because it allows us to evaluate line integrals that would otherwise be impossible to be able to discover what they evaluate to. So it truly was a monumental achievement of the human mind and is impacting society and humanity to this day. To this day, every time you use a piece of technology that has anything to do with electronics, you can thank Green's theorem for that. Okay, so let's evaluate a line integral using Green's theorem. Okay, let's let C be a triangular closed curve like so. Let's say this is a 0, 1. 1, 0. Let's say this is a 0, 1. Here's the origin. And let's say the curve is moving like so. So it's a positively oriented curve. Okay? Meaning that this right here is given by 1 minus x is equal to y. It's a function with negative slope, but with y-intercept 1. Let's find the line integral. Well, Green's theorem tells us that we can do this. So we can just call this thing in front of the dx rp. We can call this thing in front of the dy rq. What do we need to do? We need to say partial q, partial x. What is that? Partial q, partial x is just a y. partial p, partial x, oh no, partial y, partial p, partial y is 0. Isn't that beautiful that it decomposes to just a simple 0? Notice that our integral then, this integral, will then equal the double integral on this region D, on this triangle, of these two simple expressions subtracted from each other. So it's q minus 0, so it's just y dA. So then we just set up the double integral based off of the parameters we have for x and y. Okay? So for y, it ranges from 0 to y equals 1 minus x. And from x, it ranges from 0 to 1. And you're just integrating y, dy dx. That is as simple as it gets. Okay? So once you do the integral, this ends up equaling 1 over 6. Green's theorem allowed us to integrate that very easily. Very easily. And thus it is a very powerful theorem. I should probably not erase that. Let's just keep that up there. Here is an example of a line integral that is not able, you cannot actually evaluate such a line integral without Green's theorem. Okay, let's take C to be a circle of radius 3. Well, let's also, if we're going to integrate about a circle, why don't we switch to polar coordinates? We transform x to a r cosine of theta. We transform y to a r sine of theta. And we transform our dA, which is the product of the dx and dy, to a r dr d theta. Okay. So that line integral with the power of Green's theorem, we also need to compute partial q, partial x. So here's our q. p dx of this thing is a partial q, partial x. So actually, this is q. Partial q, partial x is just a 7. Partial p, partial y, this is our p. Partial p, partial y is just a 3. So Green's theorem says that this whole line integral is the same thing as the integral about that circle with just your 7 minus your 3 dA. Okay? So the dA turns into an r dr d theta. Your integral, its parameters about the r and the theta. For r, it ranges from 0 to 3. And for theta, it ranges from 0 to 2 pi. And all you get is just your 7 minus 3, which is a 4. Okay? That is quite an easy integral to evaluate. This ends up becoming 36 pi. Okay? So, that is that. There's more to Green's theorem. There's the extended Green's theorem and how you use that. That is expected of you for you to teach yourself. I will expect you to be able to do homework problems based off of it, and it very well might show up on the exam. But as of now, we are caught up as much as we can due to the ice storm. So let's see how it goes. I may upload more videos outside of class to try and get us to the end of the book. The book is over at section 13.8 on the divergence theorem, I believe. Yes. So keep up the hard work and let's finish strong.